Good day, everybody. Last class, we were able to start a series. I'm still continuing chemistry today. And in this series, we're able to look at oxidation number, redox reaction, reduction and oxidation reaction. One thing we learned about redox reaction is the fact that they are both reactions that occur simultaneously in a chemical reaction. We also said that reduction is the gain of electrons, and we said oxidation is the loss of electrons. Now, we're able to balance a redox reaction in an acidic medium. So today we are going to be considering, we're going to continue today. We are in series two, and hopefully it's to end next week. So I advise not also miss next week class too. So today we're going to be looking at electrode. But before we enter electrode, recall I said that oxidizing agent and reducing agent can be identified. We learned how to identify that last class. But one thing we need to also know that we can also test for oxidizing agent and reducing agent. Now, the test for oxidizing agent. How can we test oxidizing agent? Number one, the first thing we have there is action of iron 2 chloride. That is FeCl2. If you have a substance that you think is an oxidizing agent, you pass it through a solution of iron chloride. And what happens is that we have Fe2 plus get oxidized to what? Fe3 plus. So when this happens, we say that the substance is an oxidizing agent. But an indicator to this is when the Fe2 plus ion, which is green in color, changes to Fe3 plus, that is brown in color. When that happens, we say, yes, this is an oxidizing agent. It is an oxidizing agent. So once again, green to brown. Brown. So on hydrogen sulfide. Action on hydrogen sulfide. What the hydrogen sulfide is H2S, which is known for its rotten egg smell. Now, what happens is that if you look at the H2S, from what you can see in this slide, a yellow sulfur is deposited. Yes. When a yellow sulfur is deposited, we can conclude that that is an oxidizing agent. But what is common there is the fact that it moves from S2 minus to sulfur in its normal state. So sulfur to the movement of sulfur S2 minus, that is H2S, to sulfur in its normal state is when that happens, we see that is an oxidizing agent. And how do we know that? We see what they call a yellow sulfur deposit. A yellow sulfur deposit at the edge of the test tube or in the test tube. See when you see that, this is an oxidizing agent. This is an oxidizing agent. So you're able to what to identify to test for oxidizing agent. Now, the next thing you need to do is how to test for reducing agent. Very, very popular question. The test for reducing agent, and that's what the use of KMNO4. KMNO4. What do? You carry your solution of KMNO4, you pass your reducing agent in the KMNO4, and what happens? It happens that KMNO4, that is from MnO4 minus to Mn2 plus. This is from +7 to +2. And what happens is that we observe that the purple color of MnO4 minus is decolorized to colorless. When that happens, that is a reducing agent. So what happens is the fact that we have a purple color going to what? A colorless. So when this color change happens, that is an identification, or that is clearly telling us that what it is a reducing agent. Hope you are all following. A reducing agent. And with that, we conclude the last series. We can start this new series, Electrode. Very nice concept, electrode. We have gone to electrode potential, but let's first understand what electrode is. And from what you can see there, let's consider a metal piece inserted into a solution. A metal piece inserted into a solution. Let's say this is the metal. This is the solution. solution. Now, what happens here is the fact that as far as this metal is present in this solution, what goes on here is what they call, so we have what they call a redox reaction we occur in this. So it's the metal itself loses electrons, the solution gain electrons. All these movement of electrons left and right is redox reaction, and that is one of the, because the reason why it's happening because of what they call the presence of an electron. What you can see there, an electrode is made up of the oxidized form of a species in contact with its reduced form. It is a reduced form. If I'm considering this is zinc 2 plus, for instance, and zinc. You can see that it's in contact with its what? With its oxidized form and reduced form. Oxidized form and reduced form. And this is what? This is a couple. A couple. We call it a couple, an electrochemical couple. So zinc 2 plus to zinc. When you have something like that, you can conclude that it is what? An electrode. So we observe that a contact is established between this electrolyte and the surface of this electrode. And the surface of this electrode, there's a contact there. There's a contact there. And when this contact is established, what happens is that we observe what they call movement of electrons. Movement of electrons. And during this procedure, you can have an inert material to prevent the mixing or to establish what they call the electron neutrality of the cell. And what happens is that you need something like platinum and graphite. Or sorry, for such, you can use what they call ammonium chloride for such thing there. And you can see for what they said earlier on, that you need a material that can serve as a collector of electrons. And such material can be what? Or graphite. Now, so common types of graphite, common types of electrode rather, includes, we have a lot of them. One of them there is that a metal in contact with its aqueous form, very, very popular. So when you have Mn2 plus, Mn2 plus, or MnN plus, MnN plus, let me say Mn plus and M. That is telling us what? That is telling us that a metal is in oxidized form or in the reduced form. So from that, let me bring out something quickly. Earlier on, I used zinc 2 plus and zinc. This is what I mean by that. So if I have MS giving me M plus and M plus electron giving me M solid. This is in aqueous form. This is also in what? In aqueous form. Now, we can see that this itself is oxidation. And this is what? Reduction. Oxidation, reduction. And from this, we form what they call oxidized and reduced species in this couple here, these two couples. When that happens, we say that is what? An electrode. You can see it with iron. You can see it with zinc, chromium, a lot of metal, a lot of them. Now, let's see electrode potential. For what they said there, they said constitute an electrode is usually given, that they give a potential. That is very, very correct. That is very, very correct. Now, each metal we're using here, there's always a potential of such metal. So if you have interest of a particular metal, maybe zinc, copper, or anyone, there's always what they call an electrode potential. And it is established between the metal of interest, like they said, the potential is the electrode potential of the electrode of interest. So the electrode of interest, the potential shown by such metal is called potential. It's called the electrode potential. So we need to know that this electrode potential I'm talking about here, it can be coupled together with a reference electrode. And that reference electrode is said to have an electrode potential of what they call 0 volts. 0 volts. And from that, we can talk about the call a standard electrode potential. A standard electrode potential. Very, very important concept. Affected by 1, concentration, 2, temperature, and 3, the overall energy change. Very good of that question. They can be asked sometimes about something like that, and you need to always note that the overall energy change, the concentration, the temperature are very, very factors that affect the standard electrode potential. Now, like I said, we have a metal that has an electrode potential. If you compare it with another, if you want to compare it with various metals, we need to know what they call the standard electrode potential of such metal. You need to know how to do that. And for you to measure the electrode potential of that. And what we go next is what they call the measurement of electrode potential. And electrode potential can also be what? Be said to be what? E naught. E naught. E naught. The measurement of E naught. So we consider an apparatus. You see the apparatus, 2 beakers. 2 beakers. And one of the beakers, we have a metal placed in it. Same with the other beaker. Connected to a voltmeter through a wire. Now, we also note that the metal that is in the beaker itself contains electrolyte. It contains electrolyte. And the metal, we can look at the drawing. The first electrode is called zinc. The second electrode is called what? Hydrogen. Hydrogen that is placed on second is called the reference electrode. It is placed there with regard to the fact that you want to measure the electrode potential of zinc. So I want us to follow and get this gist very, very well. So you want to measure the electrode potential of zinc, you need to place what they call a reference electrode. A reference electrode. And what happens there? You create what they call a salt bridge. And I tell you that it's something that is used to maintain electron neutrality of the cell. I give an example as ammonium nitrate NH4NO3. Such solution NH4NO3 is called a salt bridge. Very, very important. So you need to maintain what they call the electron neutrality, that is to prevent the mixing of all these electrons. You can see that the electrons is in the first beaker, second beaker. So the movement of all these electrons need to be maintained. You need to create what they call an equilibrium. And that is what salt bridge comes into play. And let's look at the beaker there. You can see that it contains zinc. It contains 1 molar of the solution there. And we recall that the electrode always contain the oxidized and the reduced form. And that is why we see the zinc and the zinc sulfate solution present there. You can see the oxidized reduced form there. Now, the next one by the right-hand side is hydrogen. And the electrode used there is platinum. Platinum electrode is used there. So we observe that hydrogen gas is given out. And that is what is used for the measurement of the electrode potential of zinc. Now, moving forward, we can see that you can look up, you can see 0.75 volts. That is the readings from the voltmeter. The readings from the voltmeter. The next thing to consider now, they said, from what they've said earlier on, that the zinc electrode in the figure consists of zinc metal in mass at a solution of 1 molar zinc nitrate. This is connected to a She. I've said earlier on, connected to what? A She. What is that She? Standard hydrogen electrode. Standard hydrogen electrode. That's what they call She. Through a voltmeter. So I've said it earlier on. I'm not trying to recap all what we said earlier on. Through a voltmeter, which is made up of hydrogen gas at 1 atm, passed over a platinum electrode in mass in 1 molar HNO3. Now, we need to now note. Now, we have that. We've seen that apparatus there, but let's break it down. Because we have what we call the anode, and we have what we call the cathode. The anode and the cathode. Anode and the cathode. At the anode, we observe that zinc at the anode. What happened at the anode? We can see zinc solid giving us zinc 2 plus. So oxidation occurs there. Oxidation occurs there. Oxidation. Oxidation. Oxidation occurs at the anode. And at the cathode, we can see 2H plus aqueous plus 2 electrons. That is H2. And what happens there is what they call reduction. Reduction. That's what happens at the cathode. Now, you can see that with that, we can use that to measure the standard electrode potential of zinc. But first, we need to know the anode and the cathode. And from there, we have what they call an overall net equation. That is gotten by what they call the balancing of this equation there. And that is what? That is zinc solid plus 2H plus aqueous. This will give us zinc 2 plus H2. You can clearly see from this that what do I do here? I more of like sum them up. So later on the left-hand side, so later on the right-hand side, I can what? That goes away. And I sum everything up. And this is called the overall net reaction. And from this, you have what they call the potential difference, which is known as what they call the electromotive force, EMF, sharp, EMF. Please don't forget this, EMF, electromotive force. So how do we know electromotive force? From what we've done here so far today, guys, the electrode potential, that is E naught, standard electrode potential is E naught. E naught means standard electrode potential. E is electrode potential. So that is equals to what we call E oxidation or cathode, sorry, E cathode minus E anode. And at the cathode here, you can see 2H plus. 2H plus. And the anode, you can see zinc. Guys, this is the formula for you to determine the electrode potential, the potential difference of the one. This variable is called the EMF or the standard electrode potential. Anyone want to call it electromotive force or standard electrode potential? And this is formula for it, E cathode minus E anode. Very, very popular formula. And then we go to the next slide. What you can see there is you can see that the anode is zinc. The anode is zinc. And from what you read from the voltmeter that time, we observed that from the voltmeter, let me show you something. From the voltmeter, we observed that from the voltmeter, you observe that the E of that zinc itself, E naught, the E of that zinc is 0.76 volts. 0.76 volts. 0.76 volts. What you can see here. Now, doing that, if for the cathode, we establish the cathode is the cathode is the hydrogen and the anode is the zinc. Now, knowing that, I can easily solve for that. And what happens here is that we say 0 minus, so this is minus 0.76 volts. Sorry, you get 0.76 volts. And this can be said to be 0.76 volts for the E naught of the cell. E naught of the cell, 0.76 volts. Now we can see that this implies that a standard reduction potential of minus 0.76 volts can be assigned to the reduction of zinc 2 plus to zinc minus. So it's gotten not like we're calculating it, it's a standard value. So it's minus 0.76 volts. So we got that based on the fact that the reference of hydrogen was measured and that was already at minus 0.76 volts. But I want to now determine the E naught of the cell, because when we do that, we establish what they call a potential difference that is called EMF. EMF. E naught. So from that we have, so the E naught of the cell, E of the cell is 0.76 volts. And with that, we can use this method to determine the standard electrode potential or the EMF of various cells. And that's why we need to understand some basic things about this. We need to understand the fact that no matter the cell, what you need to know is the reduction potential of these cells. If you know the potential, the electrode potential of each cell, then we can determine it. And that's where we go to what we call electrochemical series. Electrochemical series. And in the electrochemical series, you see various metals. And what you observe about these various metals is the fact that these various metals have their individual electrode potential with reference to the what? Hydrogen electrode. Reference electrode. And that is what? 0 volt. Is 0 volt. That is 0 volt. So from that, you need to observe one important thing about that. You need to observe the fact that you can determine the EMF of various cells. And with that, before we conclude the class, let's quickly bring out something out. I wanted us to bring out something out as reference to what we said earlier. Now, if you consider a cell, and we know this metal is a metal strip, the electrode itself. We have an electrolyte. This is the electrode. I wanted to bring out something because people do get confused at times. This is the electrolyte. You can see one of the electrolytes because I observed something in the slide. And what I observed was the fact that the electrolytes are in aqueous form. And to answer your curiosity about this, I decided to let me bring it out and talk about it. Now, electrolyte itself can be said to be different from conductors. Yes. Conductors can be a metal can be a metal that conducts electricity. But electrolyte is said to be a solution. It can be in molten form too. A solution or a molten form that can conduct electricity. That means we believe that when we dissolve a particular metal in solution, such solution can conduct electricity. And that is the reason why, I think I said that in the last class, that's the reason why you can easily put your wire in a lime or lemon and you can easily ignite bulb. Now, what you need to know about electrolyte is the fact that let's consider NaCl. NaCl is a salt. And fine, it is a salt. So we observe that when this NaCl is dissolved in water, it becomes NaCl aqueous. Aqueous in the form that its solvent is water and the solute is what? NaCl. And in solute, in its aqueous form, it breaks into Na plus and Cl minus. Na plus and Cl minus. And say this Na plus is the what? Cations. Cl minus is the what? Anions. Cl minus is the anions. And we recall earlier on, we have what they call the anode, we have what they call the what? The cathode. There is movement of the anion and the cation towards the anode and the cathode. That's what I'll talk about in the next class. So I don't want to just open our mind to that and get us refreshed for that. So expect that the next class, so don't miss the next class. We'll talk about something like that. We'll be trying to know how the movement of these electrons are. Very, very important. So the electrode, electrolyte, and the sum of all this is what we know as what we call electrolysis. Electrolysis. Important concept in this part. Electrolysis. Electrolysis is very, very important. You see electrolysis in virtually everything we do in life. For those that, for you see, for example, if you want to quickly go out, so you have a car battery. Your car battery is made up of what? Electrolyte. And the concept is what? Electrolysis. So, now, the other one about this metal strip. This metal strip being an electrode. Someone will say, okay, what is this metal strip is just a metal hanging out in the street. We have a lot of metals hanging out in the street. Examples of metals are your nails. Sometimes when you want to pick something on the ground, you observe, you see nails that are in rusted form. That is, if you don't see one that is new or something. And we observe about those nails in the rusted form. We observe the fact that those nails, they have what they call gain moisture. And when they gain moisture, they rust. And that concept is the concept of what they call corrosion. Concept of what they call corrosion. And in corrosion, consider rusting. Consider rusting. And when those substances rust, is an electrolytic process. Yes, it's an electrolytic process. And those are the things we'll talk about in the next series too. Corrosion. Corrosion. For those that live in that are mostly seen when they are making gates or a metals material, you see that paint is used to what? To clean or to is used on the metal. Why? Because you want to prevent what they call corrosion. And that is why, and it is being said that every year corrosion is people say it is very expensive. Why? Because there's lots of lives, there's lots of properties. You could also that today that bridge just fell. Why? Because of corrosion. And that's why the federal government always spend lots of money in what? In maintaining good structures. Why? Because of what? Of corrosion. So there's always money that is being pumped into corrosion for them to what? For them to repair, remodel, and do various things to metals. And that's why we need to understand this concept very, very well. I believe this part is something that have a lot of questions. So I will always want to give room for those questions. And I want us to feel free to type those questions. Now, after you watch the video, please type those questions. And before we start the next class, before we start the next series, the next class for the same series, we are going to look for ways to answer such every question. And please don't miss the class. And with this, we end the class here. The next series, we'll be considering the electrochemical cells, and more importantly, we'll be able to what? Understand the movement of these electrons. Please, very, very important. So thanks for your time, guys. I really appreciate it. We'll see you next class.